101, a player passes a 0.6 kilogram basketball down the court for a fast break. Ball leaves the player's hands with a speed of 8.30 meters per second and slows down to 7.10 meters per second at its highest point. Ignoring air resistance, how high above the release point is the ball when it is at its maximum height? So, situation here kind of looks like this. Got our person, got basketball, throw it up, not too high, and does something like that. Initial velocity of 8.3, and to up here it slows down to 7.10. Now, they say, how high above the release point is the ball when it's at its maximum height? So our release point, is right here. And we want to know, how high above that release point it wound up. So any problem like this, where you have things going up or down, speeds, changes in height, is going to be a conservation of mechanical energy type problem, which always gets set up like this. We have the initial gravitational potential energy, just put the G there, you don't put the G, plus KE initial is equal to PEG initial, sorry, that should be final, plus KE final. Fine. Okay. So right off the bat, we can cancel some of these guys out. Considering that they're asking how high above the release point. Okay, the release point, what was our height when we released it? If this is where we're measuring heights from. It's going to be 0. So which term up here can I cancel out? Which potential energy? We can cancel out the initial potential energy. Are there any others we can cancel out? Doesn't look that way. Okay, we have an initial speed. It is some height above where we released it from, so gravitational potential energy is going to be there, and it's still moving. So all these terms are going to remain. So now we can plug in the equations for these. 1/2 mv initial squared is equal to mg h final plus 1/2 mv final squared. Now, we are solving for h final. That's what we're looking for. Right now, do we have enough information to go ahead and solve for that? Absolutely. Now, each of these terms have an m on them. So even though they gave you the mass here, what can we do? I mean, you could plug the mass into each of these terms and divide it by itself. Or you could just do what to make life a little bit simpler? Take out the m's, divide both sides by m, and they all cancel out. When every term has an m, or any term on it, or any variable on it, I should say, you can go ahead and cancel them out. See what I'm talking about? At least that was a good picture. Okay, so the m's all cancel out, so we're just left with 1/2 vi squared is equal to g h final plus 1/2 v final squared. Okay, so plug in numbers. 1/2 the initial is 8.3. That's getting squared. G, 9.8 meters per second squared. H final, that's what we have to solve for. Plus 1/2. V final is 7.10 meters per second. And that's getting squared. We could do our math there. And we do our algebra there. Take this term over to the other side, subtract it, then divide by 9.8. H final should be about 0.94 meters above the release point. Alright, so that was 101. Moving on to problem 102 here. Again, 101 is a really good one to know for the test. It's a pretty standard conservation of mechanical energy problem that might get covered on a test or something like that. But on 102, it's a little bit different problem. We have a 5.7 kilogram rock being dropped and allowed to freely fall freely. If the initial kinetic energy, or excuse me, find the initial kinetic energy, the final kinetic energy, and the change in kinetic energy. For A, the first 2 meters of fall, and B, the second 2 meters of fall. So, first, it says the rock is dropped. So for part A here, or even, this part, where it says find the initial kinetic energy, for part A, it says the first 2 meters of fall, so it's dropped, so initial kinetic energy is 0 joules. And the final kinetic energy, meaning the kinetic energy that it has after it's fallen 2 meters, so we're dropping it from rest, it falls 2 meters, that would be the first 2 meters, and then in part B, they ask for the second 2 meters. So we are finding the kinetic energy here, 0, the kinetic energy here, the change in that section, and then the kinetic energy here, the kinetic energy here, and the change in that section. So now KE final for the second part could be 1/2, for part A here, 1/2 mv final squared. Now we have a mass, we do not have a speed though. So that's tricky. We want to know the speed right here. That's the VF that I'm referring to. So anytime we don't have a speed, but we have a distance it fell, we know that it's falling at a rate of 9.8 meters per second squared, and it was dropped from rest. So we gotta go back into our bag of kinematics equations and solve for V final. So we want to know V final. We know delta x is -2 meters. We know that G is equal to -9.8 meters per second squared, and, it's just 9.8. The negative's already in the equation. And what else do we know? And VI is equal to 0. Looking at our kinematics equations, we can pull out this guy. VF squared is equal to VI squared minus 2G delta x. That's just the one for free fall. If it was, the normal version of it is plus 2A delta x. But either way, same thing. So VI cancels out. VF is going to be equal to the square root of -2 times 9.8 times -2, which turns out to be the square root of 39.2, which I believe is 14.6 meters per second, if I'm not mistaken. 39.2. That's not right. 14, what am I saying? Thinking of a different problem. 6.26. Totally the same thing. 6.26 meters per second. So now that we have that speed, plug that in here. 1/2 the mass, 5.76 times 6.26 squared. Plug that into our calculator. 5 times 5.76. About 112.9 joules. That's our final kinetic energy, which means that our change in kinetic energy is KE final, 112.9 minus 0. So the change in KE is 112.9 as well. Okay, so that was kind of an annoying process. So do we have to do that whole thing all over again for the second 2 meters here? No, because your answer for B are going to be the same 3 things. Well, not the same 3 things, but your initial kinetic energy is going to be 112.9 joules. Your final kinetic energy is going to be 112.9 more. So your change in kinetic energy for that section is, again, going to be 112.9. That's really what we're ultimately trying to see here, is what the change is. Point is that we lost the same amount of potential energy in this section as we did in this section. Which means that if we lost the same amount of potential energy, because we lost the same height, that means we must have gained the same amount of kinetic energy. So in the first 2 meters, we gained 112.9. In the second 2 meters, we gained 112.9 again.